All right, so today we're going to continue where we left off. We started talking about quicksort. I gave a demonstration of it. And remember that it is far faster than selection sort. This is a quasi-linear sorting algorithm, meaning that it makes about n log n comparisons instead of selection sort, which required n squared operations in order to get it done. And we're going to see how much faster that is when we implement it, but we're not going to actually implement it. Instead, we're going to look at how you actually do this stuff in practice. You don't actually roll your own algorithms, right? Generally, you don't need to do that because it's part of a standard library. If you did try to roll your own and implement your own selection sort and implement your own quicksort, then you'd have a lot of copy pasta for different types. You'd have to have my quicksort implementation for integers, my quicksort for doubles, quicksort for airports, et cetera, right? And not only that, but you'd have a lot of testing and debugging ahead of you because you're implementing your own doing your own way, and it's going to have to be a lot of infrastructure in order to get anywhere close to what the quicksort algorithm that's built into the C library has had over the last 50 years, right? So we actually have a term for this. This is from cryptography mostly. But we say don't roll your own. Don't roll your own solutions. Use the solutions that are part of the standard libraries, right? And so we're going to use those, but they're built in. They're generic. There's not one for integers and another for doubles and another for strings, right? They are what are called generic functions. We've seen this before. There is not a malloc for integers, a malloc for doubles, a malloc for strings, right? There is one malloc. That malloc returns a generic void pointer that you can treat that memory however you want. The idea here is that we are going to have one sorting algorithm called qsort that sorts integers or it sorts doubles or whatever, right? We just need to tell it how to order, right? And for that, what we need to do is we need to define what's called a comparator function, okay? So let's talk about comparator functions, and then we'll come back to how to actually use quicksort, all right, or qsort. A comparator function is a function that takes two things. Note there that I am emphasizing things. I'm not saying that they're integers. I'm not saying that they're doubles. I'm saying that they're things A and B. And it returns the following. It has the following signature here. It returns something negative if A is less than B. It returns 0 if A is equal to B. And it returns something positive if A comes after B. In other words, B is less than A. That's another way of putting it, okay? You've seen this kind of pattern before with string comparisons. If you have this string and this string, strcmp returns something negative, positive, or 0, depending on the relative ordering of these things. However, it's a little bit different because in C, a comparator function has to have the following signature. Let's do it this way. Come on. Oh, okay. Everything just froze up for a second. All right. Oh, yeah, now we're good. Okay. The signature of a comparator must be the following. It will return an integer. Again, something negative, positive, or 0, right? It doesn't matter what the name is. That's just a placeholder name. But it takes two generic items here, right? Now, what are these? These are not necessarily integers. These are not necessarily doubles. They're anything that you want them to be. This generic void pointer here, like we used with respect to malloc, right? It returns a generic void pointer. And then we casted it to the type that we wanted. We wanted this to be an integer array, or we wanted this to be a double array, right? Well, now we're doing the same thing, but with parameters here. And by the way, what does the constant front mean? We're not going to be making changes to it, right? So it returns an integer following the pattern above, as I said, and it takes two generic void pointers as arguments. It doesn't take two integers, it doesn't take two doubles, etc. And the const keyword ensures that there are no changes made to the contents of those memory locations. It's just going to look at the A and B and say, oh, A comes first or B comes first or they're equal. Right? It's going to tell, the reason that you want to do this is, we'll see a diagram here in a second, but the quicksort function is going to have to ask a question about these two things of, should I sort these, right? Should I swap them because they're out of order, right? Or should I leave them alone because they're equal or they're already in order, right? Or if you're doing that partitioning, you're going to compare that pivot element to another element, and you need to determine, does it go into the left partition or does it go into the right partition? And this pattern here will be able to tell it that. Okay. All right. So once you have that function signature, you actually need to implement it. Inside the function, you follow the generic this pattern, this general pattern. Right. First of all, you need to cast them to those generic void pointers to the actual types that you're comparing, just like we did with malloc. Once we got that generic void pointer from malloc, we casted it into an integer pointer to treat it as an integer array, or a double as a double array, right? Once you've done that, then you can actually set yourself up for an if-else-if statement, right? To return something negative, 0, or positive, depending on the relative ordering of those arguments, okay? So let's go back to our code, and let's actually implement a comparator function for integers, okay? Let's come up to the top here, and to do document this, right? Don't forget your documentation. But now I'm going to document my comparator function. This is a comparator function, a function for integers that orders them. Note here that I didn't say sorts them. That would be wrong. Quicksort is going to sort them. We just take two elements and we're ordering them. That orders them in ascending order. In other words, 5, 10, 15, 20. Not descending order, which would be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay? So what is my signature here? Remember that it has to return an integer. Okay? What should I call this thing? Well, I can't just call it CMP because I'm going to have several comparators here. And I want to make sure that this has an appropriate label. I'll just go ahead and call it CMP int. And I'll also go ahead and add ASC to it for ascending. Okay? Now, what are the arguments that it should take? It's going to compare two integers. So should it be integers A and integers B? Nope. That is not the signature of a comparator, is it? All right. All right. Well, should it take two const int stars A, const int star B? Once again, is that a comparator? No. It has to be void, right? Otherwise, it's not considered a comparator function, and you won't be able to use it appropriately. All right? There is my function signature along with the name. Now let's go down and actually implement it. Okay? Come on. There we go. Okay? The first thing that I do is I cast those generic void pointers as the actual types that we're trying to compare. I could cast them as doubles, but then that would be a double comparator, right? So the first thing I'm going to do is I'm going to establish two variables, const int star x and const int star y. Right? I can't call them A and B again, can I? Because those names are already taken. And then I'm going to make a typecast here, const int star of A. Right? No space there needed. Const int star B. Right? I'm forcing A and B to become integer pointers, just like as if I had called malloc, right? Malloc. That returns a generic void pointer, right? But then we force it to become an integer pointer, right? For the purposes of treating it as an integer array. Here I'm forcing A and B to become integers instead of generic void pointers. Once I've got those, I can now do the second part. I set up an if-else-if statement to return the appropriate value. Right? So if x is less than y, then that means that they are in order and I return something negative. Okay? Now, is that how I compare two integer pointers? Yeah, I mean, they could do this, but what is it actually comparing? Is that memory address less than that memory address? Not are the contents stored in that memory address less than the contents stored in that memory address. So how do I take a pointer value and treat it like a regular old variable so that I can examine its contents? Star x, right? And star y. Okay? That's the dereferencing operator. If it were a regular variable and I wanted to change it into a pointer variable, that would be ampersand. Right? Else if, just the opposite, if the thing stored in x is greater than the thing stored in y, then they are out of order. And so I should return something positive. Now I could mash my keyboard here and just return something positive. Why? Keep it simple, right? The KISS principle, right? Just one is good enough, right? By the way, could I return 0.5? I could, but what happens? It's an integer truncation, and so it would end up being 0, and that ain't right. It's got to be positive here. What's the only other possibility? Return 0 because they are equal. Okay. Generally, what you want to do is you want to hold off equality for the last one, for the last check there. This will also work for doubles here. Okay. All right. There's my first comparator. Now, eventually, I'm going to use this as in a call to QSort, but before we do that, let's do another comparator. What if I want a comparator that doesn't go in ascending order, but I want it in descending order? Right? That is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Right? So first of all, I should change the name to desk, right? Descending. Right? And I'm going to go ahead and try to copy and paste this and just rename it, at least initially, desk, right? What would I change here? Yeah, the inequality. This one would become greater than, and this one would become less than. Right? Seems like a lot of copy-paste just to change two characters to me, right? We already have one that orders them in ascending order, right? What if I called that one int result is equal to that of A and B? Right? Now, I've got something that is either negative, positive, or 0, depending on the relative ordering. I want to flip those around. What could I return now? Yeah, -1 times result. Right? The positive one becomes -1. The negative one becomes +1. And what happens to 0? It stays the same. Cool trick. I didn't need to declare a variable for that, though, did I? Nope, I could just go ahead and return that. All right, there we go. Okay. Can we get this down even further? If you've ever heard of Code Golf, it's a game that you play where you've got a problem to solve. Right? And in golf, like the smaller score wins. And so if you can do this in 10 lines of code, great. But if you can do it in 5 lines of code, that's even better. If you can do it in 1 line of code, that's even better. If you can do it in 1 line of code with fewer characters, then you're still now you're winning, right? Do I really need to multiply? I could just say negation. I'm going to go one more here. What if I don't negate it all at all? What do I do? A and B. Flip them. Flip A and B. And that's it. Right? And that's as far as I can go. Right? I mean, you got to have the return statement there. You've got to have the function call, and you can't shorten A and B any more than that. Right? I get white space doesn't count. Right? So you can't get it that down. Right? All right, great. Now I've got 2 comparators. Let's go ahead and now look at QSort, quicksort, the implementation, in order to now use those comparators. Right? Once you have a comparator function, then you can start calling the QSort, which is in the standard library. stdlib, that's where it is, so you're importing that already anyway. Right? Here is the function signature. Okay? It is a void function. It doesn't return anything. It will modify the array that you give it. There are 4 arguments here: base, nel, size, and compare, along with brand new syntax that we might get to after the break. Right? Let me explain what each one of these is. Right? Well, that first one is pretty self-explanatory. The base is the array of elements that you're trying to sort. Is it an array of doubles? Is it an array of integers? Is it an array of strings? Yes. Right? It's a void pointer. Right? It can take any type of array. Right? Okay. Nel is short for number of elements. Elements. That is the size of the array. Okay. We have to do that with all of our functions. If I'm going to pass in a function, an array to a function, and have it sum all the elements, or take a mean, or something like that, then I have to tell it how many elements are in there, how big it is. Right? Size is the number of bytes that each element in the array takes. In other words, i.e., what we're going to use is size of. Now, why does it need to know how many bytes are in there? Quicksort is going to rearrange our array. It's going to look at, say it's integers. It's going to look at these 4 bytes over here and these 4 bytes over here, and it's going to ask the comparator function, are these in order or not? And it's going to say, no. Okay, great. I need to swap them. That means I need to copy 4 bytes over here to a temporary variable, copy these 4 bytes over there, and then copy the 4 bytes over here. What if it's a double instead? Now it's not copying 4 bytes, it's copying 8 bytes to a temporary variable, taking those 8 bytes over here and moving them over here, and taking those 8 bytes and putting them over there. What if it's an error port that takes 42 bytes, right? It needs to take those 42 bytes and those 42 bytes and swap those, right? So that's why you need to tell it how big each element is. And then finally, compare is a function pointer to your comparator function. We're going to look at more on that later. Just for now, know that it's the function's name, okay? Whichever comparator that you want to use. Right? Let's go ahead and take a look at an example over here. I've already set everything up like we've had it before. Let's go ahead and review. Where's my main? Come on. There we go. All right. So what I've got here is a variable n that I can control. And then I'm generating a random array of size n. I'm printing it out, and then I call my sorting algorithm. Here it was selection sort. And remember that it was taking forever, right, on an array of size 10,000 even, right? And then we're actually going to time this, right? We are going to benchmark each one of these things. For now, though, I want to just call quicksort to make sure that it works. Qsort is the name of the function, right? The first argument is the array that you're going to be passing in, which is my array right here. The second argument is the size of the array, which I'm storing in n up here. The third argument is the size of each element in the array. Because it's an integer array, right? There it is, integer array, I use size of int, right? Okay. Now the final argument here is the name of the comparator that you want to use. In this case, CMP int ask, or ascending for short, right? There we go, there. Now if it were descending, then I would say descending, right? ASC, there we go. GCC, demo, and array. Utils, there we go. Now remember, I'm going to print it out before it gets sorted, print it out after it gets sorted, just to make sure that it works. And the computation time here is not measurable. It's less than 0, so that's why it's reporting 0 seconds. Okay? But verify, is that indeed in ascending order? Yep. Ascending order. Ascending order. Do it as many times as you want to be satisfied. What if I wanted it in descending order? Let's go ahead and recompile it with that other comparator and see that it now works just as fine. Right? Descending, descending, descending. Right? Let's just go ahead and change it back to ascending here. ASC, there we go. Let's kick it up. Actually, let's go back to selection sort here. And I'm going to go ahead and get rid of our print statements because we're about to kick this up to, let's go with 10,000 to start out with. All right? And let's go ahead and time it. Okay, 10,000 is not that many. 100,000. Oops. GCC and a dot out. There we go. Now we're starting to notice things. 100,000 here. Maybe it took 1 second before, and it's 100 times now slower because it went up an order of magnitude. Okay, no, it wasn't even 1 second. Now it's 7 seconds. If I had gone up to 1 million, predict, what did we say that would end up being? It'd be 10 times bigger, 100 times slower, and then I let it run last time, or the time before that, I forget. 700 seconds would be about 12 minutes, a little less than 12 minutes. Nope, I'm not doing that. All right, this is 1 million elements. How much better is quicksort here? Remember, selection sort would have been about 12 minutes. All right, GCC. 12 minutes versus almost instantaneous. All right. Now, there was a little bit of lag time there, but the lag time was probably generating the array. All right. Let me go ahead and kick this up to 10 million. Now, if it took 12 minutes on selection sort before, 100 times that would be 1,200 minutes, which is, I don't know how, 12, like a third of a day, so 8 hours or something, right? And I'm not going to do it with selection sort, but I will do it with, come on, there we go, quick sort. Now it's a little bit noticeable, but it's not going to be 8 hours. It's about 1 second, right? So you see, selection sort is blowing up just like any quadratic function would. But quick sort is, remember that it's quasi-linear. It's going to stay about linear, right? So if I go up by another order of magnitude here, now that's probably going to be too big. 100 million, right? GCC this. All right. It is going to be way more noticeable now, all right? There, now it's sorting. It's going to be maybe about 10 times slower because it's quasi-linear. I'd say maybe about 11, 12 seconds or so. Maybe a little bit more, I'm not sure. We'll find out here. I'm confident, though, that it's not going to take, like, more than 30 seconds dead. What would have it been for selection sort again? We were up to 8 hours. 8 hours times 10 is going to be, or 8 hours times 100, excuse me, is going to be 800 hours. How many is that? Better part of a month or so, maybe a couple weeks. I'm not doing that. Nope. All right. So let's get rid of that selection sort there. Right. So quick sort is definitely the answer here. Right. A little bit more practice. Let's see. Let's go ahead and create a comparator function for doubles that orders them in ascending order. Okay. Now, am I going to be able to reuse this guy up here at all? If I take these doubles and I treat them as integers, no, like 0.5 is going to be the same thing as 0. So I am going to have to repeat code here, right? But it's not. But it is going to be almost virtually the same here, right? So let's go ahead and call this double, right? Double ascending. The only difference is that I treat them now as doubles everywhere. Double, right? Double, 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 and double. Right? Now you might be asking yourself, well, wait a second. We've done computations before where if they were close enough, they were within 0.00001, then we said that they were equal. We don't want that in this case, right? Because we want equality, right? Like that's why we're using this else as our last argument, right? If it's not less than, if it's not greater than, then you definitely know that it's equal, right? Don't put equals first because then you do have floating point issues, right? What did I call my function up here? I don't think I named it correctly now that I think about it. Oh, I didn't name it at all. Okay. There. I'll just put it into the name. Double descending. Okay. All right, let's bring up our old book demo over here. Right. Remember that there's a structure right there. Right. Okay. Now, how would we go about creating a comparator so that we could sort a bunch of books? Right. Let me come over here and let me document it. Comparator function for books that orders them by what? We've got a lot of choices here. Right. How do we want to order them? Title, author, rating. Title. All right, let's keep it simple, and then we can build on that. By title. Okay. Now, what do you mean by title? A should come before Z, right? So, actually, let me finish out the signature here. What should I call this? Book. And then put into the name what you're comparing. By title. Right? That's a good name. Right? Now let's come down here and actually implement it. Okay. Now my first step is going to be just like I did up here. I'm going to cast them as the appropriate type. They're not doubles, though, in this case. They are books. Right? That means I'm going to have to bring in that code from before, but that's okay. We can take care of that later. Right? We're just trying to get the idea now. Right? Now, once I've got that, then I put in what the business logic of comparing X and Y's titles. Right? Now, to get the title, remind me, do I use The arrow operator or the dot operator to get the title? Arrow. Why is it the arrow? Because I got a pointer to it. Right? And it is const, so I'm not going to be making changes to it. Right? So I need to compare X's title versus Y's title. What are those things? Strings, right? Where is title? There it is. Char star. Do we already have a comparator that we can reuse that'll help us compare these two things? Yep. Int result is equal to strcmp of these two things. Right? And guess what? It's in the same natural ordering as what this is called. The A's come before Z's, and 0 comes before 9. It's the ASCII text table. Now you do have to be careful here because it is case sensitive, right? The uppercase letters all come before the lowercase letters. So uppercase Z would come before lowercase a. If that's the case, then what's the other alternative here that you have? Case CMP. This is case insensitive. Uppercase A, lowercase a, they're treated as the same. So which one do we want? We're not going to be able to actually run it today, but I'll just leave it like this for now. Once you've got that result, all you need to do is what? If result is less than 0, then I'll return something less than 0. Else if the result is greater than 0, I'll return something greater than 0. Do I need that at all? Yeah, return result. It's already something less than, or negative, positive, or 0, depending on the relative ordering of those two things. In fact, do I need that variable at all? Nope. Just return. And you're done. It's as simple as that. Okay? Let's do one more, or a couple more. Let's do books again. That orders them by author, then by title. Right? So in other words, I want all of John Stuart Mill's books right here. And then within John Stuart Mill's, I want all of his books ordered in alphabetical order according to title. Right? So that all of the author books will be clumped together. Right? Okay? Book by title, author, or author title, excuse me. There we go. So these names can be quite unwieldy, right? But let's go ahead and implement that now. There we go. All right. Very first thing that I do is typecast them. All right. Now I need to compare it with respect to the author. In fact, let me go ahead and come on. There we go. Okay, fine, down there. Right. Where's person? All right, there we go. First name, last name. All right. So first compare the last name. Now how am I going to get access to those? I need to go to the author. Right? That's because there's the author. Right? X is still a pointer, so I still use the arrow operator there. Right? But once I'm at the author, then it's a regular old structure. I would use the dot operator to get their last name. Right? Versus Y's author dot for last name. Right? There we go. Let's just call that result is equal to. Right? There. Return result. If I just did that, what would I be doing? Jack Smith and Adrian Smith would be the exact same author. Right? So if I have a tie, if result is equal to 0, then we have the same last name here. Okay? And at this point, I think I can get rid of this. Right? There. And there. Right? So if you have a tie based on the last name, then now what should I do? Yeah, let's go ahead and order by. Remember, we're not sorting here. That's Quicksort's job. We're just ordering here. We're ordering here, not sorting. Sorry. First name and first name. Right? And then return result. Well, what if it's the same last name, same first name, so that we have Frank Herbert here, right? Now Frank Herbert has 5 Dune books, right? We need to order those now, right? And how are we going to do that? By the title. So if result result is equal to 0, right? Then the result is going to end up being, oh, what am I doing here? I haven't even called the proper functions. strcmp, sorry, and strcmp. Now strcmp of x's title and y's title. There. And then I can return the result. What if I wanted to do this by author, then by I don't know what else, then by title, then rating? That doesn't make any sense. What if I had like 5 different things that I wanted to order by, right? Sort by this, then by this, then by this, then by this. Do you see if I start following this pattern, I've got an if, right? A whole bunch of, it's called nesting hell, right? Where you've now nested 5 times. Don't do that. We can actually flatten this out, right? If the result is 0, I change the result. If the result is 0 again, I change the result. No matter what, though, I return the result. So I don't need this inner if. Let's go ahead and take that out and end it there. And take that out and end it there. There. Right? That's the same exact logic, but now I'm not in nesting hell at all anymore. I'm not nesting at all. Right? I've got, if the author's last name is the same, then break the tie by looking at the first name. If it's still tied, then look at the title. Right? So all you need is a series of if conditions at the same indentation level. Okay? All right, great. At this point, I'm tempted to go back, and we've got plenty of time. We can, let's see, copy or move, copy, what was it called? Code, book, book.c here, and copy code book.h here. There we go. And let's open up the book demo. I'm going to steal code from there. There's a lot of code to steal, though. That's okay. I can steal all this main code. There we go. Let's come back over here, and I'm going to go ahead and get rid of this main. I'm just going to comment it out, but you'll still have it in your notes if you want it. And I'll replace it with this main. And let's go ahead and GCC this again. Verses. I still have verses in there somewhere. Find verses. There we go. All right, I was really doing pseudocode there. There we go. Clear this. GCC. Why author? Why are you not? Oh, because I have not included the book. There we go. So I'm going to have to add a bunch of stuff here. Book.h. That should be enough, though, right? Okay, yep, that should be enough. And then, so let's do that, and then book.c. Good. We just need to include the string library. Include str or string.h. Why do we need to include the string library? Because we're using that strcmp, right? There we go. And now we're good. Right? So that's the demo from before. I also need my file, right? Copy code, and what is it? Book data? No. My Goodreads data here. And then let's try that one more time. Okay, good. Now we're at a working state here. Now let's actually go to the main and start doing stuff. Okay? So I've read all the books in, and I print them all out. Right? There's printing all the books right there. What is the oldest book? What is the newest book? How can we collapse these two questions down and get one answer? Right? So we can quick sort the books. Right? And this will be books. That's where we're storing them, right? Or did I call it library? No, it's called library, sorry. Library. How many are in there? Num books. How big is each book now? Size of book, right? And then finally, I need a comparator. If I'm going to answer the question of oldest book and newest book, then that means I need another comparator. Let's write that comparator really quickly here. Right? So comparison function for books that orders them by year. Right? And so I shouldn't call it title, I should call it year, right? And let's go ahead and implement that really quick here. I am going to copy and paste some of the boilerplate up here. There we go. I'm glad I did this one, because now what we can do is we can do a trick, right? Generally this trick is not recommended, but I'll show you the trick and then I'll tell you why it's not recommended. X is, what was the year? All right, refresh this. What did I call it? Year. There, yeah, it is year. All right, year versus Y's year. Okay. Now I could check if X's year is less than Y's year, right? Then I will return something negative, right? Else if X's year and Y's year is greater, greater, then I'll return something positive. Else, return 0. But now let's take a look at a quick example here. 2024 versus 2025, okay? What if I were to take a difference instead? 2024, 2025, those are in order. I want to, like the oldest books to the newest books, or oldest books to the newest books, right? What is that? What is the result of that? -1, something negative, right? What if it were 2025 and 2025? 0, right? What if it were 2025 and 2024? Something positive. So I might be tempted to forego that if-else-if statement and simply just return their difference. And that will work. And it especially will work for this particular example because all the years in my database are between, what was it, 700 BCE all the way up to 2025. We haven't published any books in the future. There aren't any books that are older than 3,000 years old, right? And that'll work. Does that work in general, though, with integers? What if it were 2.147 billion and change? And the same thing, but 1, right? Actually, what if it were negative that versus that? What if you did the difference trick here? Yeah, underflow or overflow, right? In this case, it's going to be underflow because it's going to be negative 4.2 billion or so, right? And that's not going to work, right? It's going to give you something positive, meaning that it's going to give you the exact opposite of what you're expecting, right? So don't do this difference trick, right? This is the difference trick, right? Avoid it, right? It is susceptible, if that's how you spell it, to overflow or underflow. Underflow. In this particular case, though, I'm going to leave it just so that we can see that trick in action, but also because it is safe, because the numbers are small. There's no book published in 4 billion BCE, right? So we're going to be okay as far as our data is concerned here. All right, now let's come back to our main, and let's try to answer these questions that we answered before. What's the oldest book? What's the newest book? I'm going to sort them by year. If I sort them by year, where's the oldest book? It's right there at the beginning. I don't need any of that stuff. I don't need to search through the rest of it because I know that the oldest book is up there. What is the newest book? Num books -1 because of 0 indexing. There, right? Now remember, the oldest book was the Republic. The newest book is Polybius. Let's see if we get the same answer again. And we do. Right? Republic and Polybius. But now I'm doing it through sorting, right? I'm just making one call to quicksort right here. Right? In fact, let's go ahead and print them out again just to make sure that it actually worked, right? So printf. Let's do some ASCII text art here. All right, there, by year, right? And then repeat that over here. Right? You can get really, really fancy with your ASCII text art if you really want to. All right. And let's clear this out first of all. And run it. There we go. There it is. All right. So before it was sorted in whatever order it came out of the file in, but now it's sorted by year. Right. There we go. Republic, -400. Neuromancer, 126. That's probably missing data right there. That's probably bad data. Neuromancer was written in the late 80s, right? I don't know. I think that I might have put that one in, and that's why it doesn't have a year. But those are all definitely wrong. There we go. Prince by Machiavelli, 1513. Right? Then we've got Of Mice and Men, 1937, ... all the way down here to the most recent book, which is Polybius, 2025. All right. Any questions? I don't know. Let's just do one more here. Let's make sure that our other comparators work. What the most interesting comparator that I think we did was by author, then by title. Let's make sure that one worked. Let's see. After we're all done with oldest and newest, let's go ahead and Q sort. Once again, it's going to be the array that you're trying to sort, the size of the array, num books, the size of each element in there, size of book, and then finally the comparator that you want to use. I'm going to go ahead and grab this, and there we go. And this will be by author title. Right. There we go. GCC this, run it again, and let's verify that one was correct too. There, author title, Armstrong, right? That comes first. And then who's down at the bottom? Looks like Wells, Martha Stewart, and she's got 2 books in there. All Systems Read and Artificial Condition. Are those in order by title? Does AL come before AR? Yeah, right. I don't have many. Okay, there are two neuromancers in there. That's definitely bad data in there, right? I don't have many repeated authors, it looks like.
Add 2 tokens a little bit lower.
Tokens? Where? T-O-O. Oh, here, Pratchett. There. Terry Pratchett. Pratchett, and Pratchett. There, I've got 4 of those, right? Diggers, The Carpet People, Truckers, and Wings. What's a problem here? Would a librarian order them like that? No, librarians ignore articles, the, a, and. So what would we have to do? We would have to go in and detect those articles. Don't worry about that, though. We're not librarians, right? This is good enough. And where was, oh, there we go. The Fellowship of the Ring and the 2 Towers. Right? I don't have the 3rd one in there. Right? It's definitely not 9. That's, what, 1953? Something like that? Right? Yeah. I don't have the 3rd one in there yet. Right. Okay. Any questions? Otherwise, remember, there's no class on Friday because I've got a big committee meeting. We're not having class on Monday either because it's usually not scheduled anyway. And so I will see you after break, Monday after break, after which we will have 2 weeks left of class and then finals week.